Hi everyone. How was your break? And the strike. Yep, survived the hurricane. It was very exciting being locked in one hotel room with 5 adults for a day. So, don't go to Florida when there's going to be a hurricane. It's my recommendation.
Is it gone?
What? The hurricane? Yes, it moved off the coast. But it was a rough day. So, today we're going to go over all of the things in Module 5, which is these first 3 things, and then also the population mean, which is the one practical problem on homework 6. So the first 3 will help you finish homework 5, which is now due next Tuesday because we didn't have class and we didn't talk about it at all. So it's due next Tuesday. Homework 6 is also due next Tuesday. It is 15 multiple choice questions and 1 practical question. So you should have plenty of time to complete both of them successfully. Okay, so I know there's a lot of stuff to go over today, so we're going to do the best we can to go through it and see what questions you can get answered for yourselves. Any questions that you have up front before we start? Okay, cool. So the first thing we'll talk about is normal distribution. So this is based on the population of an indefinite number of scores. And it's generated from formulas, not from data that you actually collect. And the standard normal distribution looks like that little graph at the bottom there. Some characteristics, the left and right tails, so that's these sections here on the ends. Those are the tails. They continue to infinity without touching that x-axis, or this bottom black axis here. The shape is unimodal. That means it has one mode, it's symmetric, and it's bell-shaped. So if you can imagine a bell here, kind of looks like a bell. The population mean is this funny-looking U shape, which would be this value in the middle here, if you draw a straight line down from this middle value. The population standard deviation is this funny looking O shape, and that's just the standard deviation of the population. The total area underneath this curve equals 1.0. So that's important to remember when we're getting to some of the questions and examples later, that the total is 1.0. And then the area underneath this is proportional to the percent of scores. So if we drew a line down maybe about here on this graph thing, and we did the formula and ran through all that and found the area was 0.20, that would be the same thing as saying that 20% of the scores are less than this point, whatever that point may be. So if you're asked for a proportion or a probability or a percentage, they all are similar. Percent, you just have to convert to a percentage versus the proportion or area under a curve can be in a decimal. So the importance of this normal distribution is because basically everything we're going to do after this class will rely on us saying that the data is normally distributed. If we didn't assume that, then we couldn't do any of the tests we're going to do the rest of the semester. So a lot of variables we say are normally distributed. Whether or not they are, who knows, but we say they are. So a lot of the inferential tests, like the independent and paired t-test we'll be talking about next week, the chi-square, which is the week after that, the ANOVA, which is the week after that, and everything else will assume that we're using this normal distribution. And from this, we're able to determine the proportion of the distribution associated with any score. So a general normal distribution can vary. So they can have the same standard deviation, like these two on the bottom left here, but have different means. So you can tell these have different means because this midpoint is different. So one's further to the left while the other's further to the right. But if you collapse them on top of one another, they're spread out the same distance. This other picture on the right here shows the distributions that have the same means but different standard deviations. And that's because one comes up higher, faster than this other one. So one's more spread out, so the standard deviation's bigger, while the other is taller and skinnier, so the standard deviation is smaller. So in research, a lot of times we assume that we're using the standard normal distribution, which just means that the mean is equal to 0 and the standard deviation is equal to 1. So that way researchers don't get confused between different populations' standard distributions. So this has all the properties of the normal distribution. So it's still going to be bell-shaped. It's still going to have a total area underneath the curve of 1. But it also has z-scores that are measured in standard deviation units. The number of standard deviations either above the mean, this middle 0 point, or below the mean. So this indicates the distance. So a positive z-score means that your score is above the mean, or you have a standard deviation that's above this middle point, so it's to the right of the middle point. Oops. A negative z-score is below the mean, or below this middle point here. And that's important to remember when you're asked a question of what is the proportion of people that fall with a z-score of 1.5. So if we look at 1.5, it would be over here. So that means we have to look to the left of that. How many people are to the left of this 1.5? So here's an example of actually using the formula, this Z formula. You don't have to memorize it, it's posted everywhere, you just have to use it. So given the following information, that the mean is 500 and the standard deviation is 100 of the population for the SAT scores that we're assuming are normally distributed, we're going to fill in this formula. So, I think this is this, yeah, okay. So, first you're going to draw the distribution. I always recommend doing the drawing because you can visualize where your values are. So first you draw a curve. It doesn't have to be perfect, just has to look sort of bell-shaped. Then you identify this midpoint, which is the population mean, or the weird Z, the weird U number, which is 500. And then this is where you're going to draw the line for the number we're looking for. So we're looking for the scores between 500 and 600. What percent of people score between 500 and 650? So then we draw in this 650 line, and we're looking for this middle region here. So then the z-score is just, the raw scores are in yellow here, and the blue is the z-score. So right now, the z in the middle is always going to be 0, and we're looking for what the z of 650 is. So then we go to this table that is posted on D2L. It's called the z table. Now, I know it's very confusing looking, but we're going to go through it. So the columns are listed with the z values here in this very far left column. So this is when you calculate that formula out. This is where you'll look. And then these 4 rows are referring, these 4 columns, are referring to which graph you're looking for. So in the example we're looking between the population mean of 500 and some other number, which is 650 in this case. If we were looking for how many people score anything up to a 650, we'd be looking at this first column, A. If we were looking to see how many people scored above 650, we would be looking at column B. And then if we were looking between some score less than 500, but more than everyone, and so between, let's say, 400 and 650, we would use this D column. Does that make sense? Does that make it a little easier to remember? Maybe. Okay. So what we're going to do is identify the column. So we identified it's this one because we're using the mean, which is the 0 point in the middle, and 650. You don't need to memorize these formulas. They're just there for fun. Just look at the pictures. And then we're going to identify, hold on. Oh, so we have to do the actual Z calculation. So we go here and we compute this Z using the formula. So Z equals 650, which is our X, what we're looking for, minus the population mean of 500, and that answer divided by 100, which is the standard deviation of the population. And that gives us a Z-score of 1.50. So a Z of 1.5 means that there's 1.5 standard deviation units between the mean of the population and this number. So now we're going to go back to that Z table to find the probability that it's between there. So we go back to this table, and you look down this left column here to find 1.50. I know it's cut off in this picture, but that's so I don't have to flip back and forth. But if you look in the one I'll posted, you just scroll down until you find on the very left-hand side where's 1.5, and then we're looking at C because that was the picture that we determined this one was matching. And where those two intersect is your probability or proportion of the population. So in this case, it would be 0.4332. So the probability of the score falling between 500 and 650 is 0.4332. Or you can convert that to a percent. So the probability would be 43.32% that it would be between those for any given person. Does that make sense? Okay. So here's another one. Here we're looking at the score of higher than 650. So we already found out what the Z-score for 650 is because we just did that. But if you need to do it again, you just plug the numbers into that formula. Then you identify which column we're going to be looking at. So since we're looking at a number above the mean and to the right, so higher than that number, we're going to use column B. So then we go find 1.5, because that was the Z we calculated for 650. And we use column B, and where they intersect, you get this number of 0.0668. So the probability that some person's going to get above a 650, this is on the old one, not the new one, by the way. So on the old SAT, is 6.68%. So this is where it gets slightly more complicated when you're looking between two scores that include the mean. So now we're trying to find what's between 300, how many people will score between 380 and 620. So we pick out which column we're going to be using. So since it includes the mean, we're using column D. Excuse me. Then we compute the Z-score, so we use the formula. We're looking first for 620. We'll start with the higher one. Minus 500 divided by 100 is 1.2. So then we are guessing because, we're not guessing, we're inferring that because the distance between 500 and 620 is the same as the distance between 500 and 380, that 380 Z-score would just be the negative of the 620 Z-score. Does that make sense? Because they're the same distance from the mean, they just have opposite signs. So then we go to the z-table to find the probability of this. So we find the 1.2 and we go to column D, and where they intersect is 0.7699. So the probability that it falls between a 380 and a 620 is 0.7699, or 76.99%. Cool. What is the proportion between 450 and 670? I don't know, let's find out. Yay! So looking at this, we're going to look at that table again and determine which one we're going to use. So D is only if the areas are symmetric. So in that last example, both the lower end and the upper end were the same distance from the mean. In this case, they are not the same distance from the mean. So we have to calculate two z values and then add them together. So 450 to 500 will be one calculation, and then 500 to 670 will be a second. Then we'll add those probabilities together to get the answer. So first we compute the z-score. So for 450, we do 450 minus the mean divided by the standard deviation, and you get negative 0.050. Same thing for 670, you get 1.70. Then you go back to that z-table, and you find column C, and then you add them together. Except I don't know that, oh, here it is. So this is just another picture showing you what the z-score is in that picture that I drew out for 450 and 670. So then we go to the little table and we find 0.50 for the first one. So that's 0.1915 because we're using column C. And then the z of 1.70 is 0.4554. And then we add those two together and we get 0.6469. Now, we don't use a negative here because you don't have to worry about the negative in this case because it's just the distance between the mean and that number. So it's the same either way. Make sense?
Excuse me.
Yes.
In that case, because we have a negative and a positive
Yes.
for both z-scores, and if I'm calculating, when do I use the negative portion of the z-table?
Not if you're using column C. So if you're using column C, you don't need to use the negative portion. And if you're using column D, you can just use the same value you find in the positive portion. Does that help a little? Okay. So now we're going to look at what score represents the 90th percentile for SAT scores. So first we have to do some algebra and solve for x. Yay! No one likes this, but that's okay. So first we convert the percentile to the 4 decimal place probability. So since we're looking at the 90th percentile, it's going to be 0.9000. If we were looking at the 5th percentile, it would be 0.0500, and so on. So this is telling us that our value underneath this distribution of the area would be 0.9000, which is really high. That's why there's a line drawn all the way over here. We don't know what the z-score or the x-score is. That's what we're looking for. So in this case, it crosses the mean. So if you're looking at this other picture, how do we know 0.9000 is going to be here? Any ideas? So this middle line here is always going to be equal to an x value or a probability of 50% or 0.50. So since 0.90 is higher than 0.50, we know it's to the right of that somewhere. It doesn't have to be exact when you're drawing it. So we know we need to use this a value because it does cross the mean, the value we're looking for. So now what you're going to do, instead of looking at the z value for that 0.900. You're going to look down column A until you find the closest value to 0.9000. So when you do that, you'll see that here, down around 1.28 or 29, there's two values. Neither of them are exactly 0.9000. So you have to choose which one is closest. In this case, it's the 0.8997. So the z-score that goes along with that probability is 1.28. So then we're going to use that z-value to fill in the formula that we rearranged so that x equals the standard deviation, the population mean, plus the z-score times the standard deviation of the population. So if we rearrange that formula, this one, to look for x, that's what you end up with, is this. So when you fill in those values, 500 as the mean plus the 1.28 we found, looking at the table, times 100, we get an x of 628. So the SAT score that is at the 90th percentile is 628. So when you get scores that tell you what percentile you're at, this is what it's telling you, that you're at a certain z-score away from the population's mean. Questions? Does this help you make more sense of what you're supposed to do for homework? What was that? Yes. Okay, so now we'll move on to just a little overview of hypothesis testing, just so you have some basic knowledge of the terminology. So before we do that, you have to know just a tiny little bit about probability. I despise probability, so it's like the tiniest possible amount we can go through without actually doing it, but you can still understand what we're talking about. So the probability is how likely some event is to occur in comparison to all of the possible outcomes. So it's illustrated by this lovely little formula here. We're not going to do anything with this formula. That's just if you like formulas. There you go. So another thing to remember is that the sum of all of the probabilities of some outcome is 1, or 100%. So if you have if you're flipping a coin and trying to determine what the probability is, you have a 50% chance of getting a head and a 50% chance of getting a tail on every flip. So if you add those two together, that's 100%. That's all this is saying. Okay. So when you have mutually exclusive events, aka you cannot get a head and a tail at the same exact time in one flip. If you can, you're magic. So if you then combine the probabilities of one event, it would equal 1. Cool? Kind of? I'm not going to have you calculate probability because no one likes it. And I don't like it either. But why is it important? Because we don't usually have access to the entire population, so we have to evaluate our sample data using probability. Another thing to consider is sampling error, which is the difference between those statistics you calculate on your sample compared to those from the population you're looking at. Because samples do not 100% represent your population. For example, if I was going to take a sample of, I don't know, all of the students at Westchester, I'm probably not going to get a representative sample that includes if I take a sample of 100, let's say, and there's like a ton of students that go here, that's probably not going to represent every single gender, ethnicity, country of origin, state of origin, how you're currently living, if you're married or not, if you are in a certain major. So the chances of the sample being representative of all of those things are very, very low. So the sampling error measures that difference between the population, everyone at Westchester, and those 100 people that I pick. So what is the difference between that whole population and that small group that I choose? Percentages of scores in the normal curve, that normal distribution we were just looking at, can be re-expressed as probabilities, which we talked about. So it can either be a percent or it can be that decimal number. So another example showing this percentage of scores between 0 and a z of 0 and a z of 2.24 is the same thing as the probability of that a randomly selected person will have a z-score between 0 and 2.24. So this is how we test hypotheses about group scores, because we can assume that this is true. The probability of outcomes in a binomial distribution, so this is what we'll be talking about next week and on in the class, becomes larger, or it becomes more normal, so it becomes closer to that ideal bell-shaped curve as your sample size gets larger. Okay, so some hypothesis testing information. The first thing is the null and alternative hypothesis. So this first symbol here, the H sub 0, that means null hypothesis. And this other H sub 1, or sometimes it's H sub A, would be the alternative hypothesis. So the null hypothesis proposes that some change or difference or relationship doesn't actually exist. So if we were going to toss a coin for football for 12 games, maybe we are saying that out of those 12 games, 6 times it will land on heads. So in this case, the null hypothesis is that there is no difference between it landing on heads and landing on tails. So half the time it's going to land on heads and half the time it's going to land on tails. The alternative hypothesis says that there will be some difference between it landing on heads and landing on tails. So that 6 of the times it will not land on heads and 6 of the times it will land on tails. Probably some other different proportion of like 3 and 9 or something like that. Okay. So then you have to make a decision about the null hypothesis. So do you think that your answer is going to be different than the population or not? So how would you be convinced that the null hypothesis is not true? Or how would you be convinced that there is no difference between what you expect and what actually occurs? So if the statistic isn't strong enough evidence, or if there's a large sampling error, then we look for other evidence that it's not true. A low probability would mean that the alpha level is 0.05. That's what we're going to use in this class. That's the standard across pretty much everything. So there's a 5% chance that even if we find that there's a difference, it could not really be a difference. I know that's confusing, but does that kind of make sense? So if I say that I have 2 sections of this class, and my null hypothesis is that there will not be a difference between the scores in this class and the other class. My alternative hypothesis is that there is some difference between the final grades of this class and the other class. So when I do the final grade calculations at the end of the semester, I find that there is some difference between this class and the other class. Maybe the other class scored better. So there is then, based on this number here that some guy made up because He wanted to make everyone's life difficult. There is a 5% chance that even though I saw a difference between the two classes, there wasn't actually a difference in your ability levels. Does that make more sense? Okay. So basically, there's always going to be a chance that you just made an error somehow between what you found and what is actually true. All right, that was hypothesis testing. How's everyone feeling? Okay about that? Okay. I have to pause the recording so that it doesn't upload like 8,000 seconds. So hold on a second. That way you don't have to watch